All right, welcome back. We are covering chapter 3 right now. We're going to be doing chapter 3 on central tendency. So let me go ahead and get that started. All right, so for chapter 3, these are going to be things that we're already pretty familiar with. So the average or the mean, the median, the mode, and generally the shape of the distribution, what we can infer about these three values and how they're distributed. So this one should go, I think, a little faster than the last one. But let's go ahead and start walking through it. Okay. So we'll start with an overview, skip through this. Okay, so I'm going to start out with an example, and this is taken from an actual research study. I put the citation in the comments if you're interested. So here, first of all, we need to figure out what the x and the y-axis is. Down here, we have our x-axis that are our categories. So we're looking at young controls, elderly controls, and then this is going to be the main population that we're interested in. These are Alzheimer's disease patients, AD, Alzheimer's disease. What we're looking at here is their attentional control and how fast they can give a response. So on our y-axis is mean reaction time in milliseconds. And generally, the fastest that people can make a response is about 300 milliseconds. It's really hard to be faster than 300 milliseconds when you're doing like a little mouse button click. So we can see here young controls for the squares. This is a simple reaction time. So say, the researcher tells you when something comes up on the screen, doesn't matter what it is, click the button as fast as you can when you see something pop up. So that's, for example, a simple reaction time. Young controls are going to be pretty much at that 300 millisecond range here. Elderly controls a little bit slower, and then our Alzheimer's disease patients are going to be a lot slower than that. Now, what we can also do, and that's when you put kind of a compound figure like this together, we can also show choice reaction time. So when you have to make a decision about something, say you see two pictures, and you have to decide, do you click left or right button for whether or not it's male or female, or your favorite ice cream versus your favorite cookie or whatever, that takes a little bit extra time to make that reaction. And so we can see that extra time here in young controls adds up to almost 200 milliseconds. Almost comparable in elderly controls. It also slows them down, and the same type of pattern as when it was a simple reaction time. And then again, our Alzheimer's patients are going to be a lot slower than that. So this chapter is on central tendency, right? And so the point of this is we want something that represents a typical score for the group that you're talking about. So each of these circles or squares is a representative score of young controls or elderly controls when they're doing a simple task versus a choice task, right? So it represents an average or typical score for an individual. Obviously, there's going to be a range, right? Some will be faster, some will be slower. But what you're trying to do is display this in a way so that you can, like I've been saying with descriptive statistics, you can very quickly glean the information that you need. So you can see young people are faster than old people. Alzheimer's disease patients are a lot slower than either, including age-matched controls, right? So central tendency, the whole point is to have a representative score for an individual in that group. Knowing that all the individuals together are going to have a variety of different scores, but you want something to represent that group. So then the next question is, well, how do you figure out what is that representative score? One way to go about it is figuring out the centermost score. And so what is the center? If it's something like this where it's a nice normal distribution, you're like, boop, right in the middle, has the most scores, nice in the middle, splits it evenly, 50-50. I am going to call this my representative score, right? Here, when it's a skewed distribution, if you can remember what kind of skewness this is it positive or negative? Again, orient yourself, where is the tail going? It's going to the negative side, so it's a negative skew. Where would you put your typical score here? You know, you could put it up here, where it kind of either, you know, the most frequency or the biggest cluster of people. Or you're like, well, the range goes all the way down to 1, so I need to kind of represent the entire range, right? So maybe it's somewhere down here. And on this one, the central score would not even be a score. It's between these two distributions. And you can't put it over here because then you'd be neglecting these guys. So if we selected 5, this would be a good average score, but it wouldn't represent the people in either of these groups very well. And so this is why we have different ways of showing central tendency. And we'll walk through all 3 of those: the mean, the median, and the mode. Yeah. Okay, so let's first talk about the mean, because this will also be the most important one when we talk about inferential statistics. So the mean, or the average, will always be showing the population and the sample of a particular statistic, or I should rather say the population parameter and this the sample statistic. So here the population mean, which is mu, not mu, but mu, is going to be the sum of all your scores divided by how many people are in your population, right? So sigma x, we've been practicing that. Add all your scores together and divide it by how many people are in your population. If it's 30, then you do, you know, your sigma x divided by 30, and that's going to give you the average. For the sample mean, same calculation. All of your scores are summed together. Because it's the sample, we don't divide by capital N, we divide by little n. And we don't give it the mu designation, it's just capital M, not N, M. Often in textbooks, we have this notation for the average or the mean. We're not really going to use this. It's not appropriate because when it comes to especially research articles, scientific articles, this isn't used. We use mu or M to denote the average. Okay, so now a few alternative definitions, right? This was, you know, the average as far as getting everyone together, everyone's score, calculating it by dividing it by how many people are in that group. Another way to think of it is that we want to try and divide something evenly between everybody. So for example, if you have 2 pizzas, each one has 6 slices, if you're going to slice it that way, big slices. You have a total of 12 slices of pizza. This is going to be your sigma x. How many x values do I have? Or rather, what is the sum of all my x values? It's going to be 12 pizza x's. What is our n? What is our population? 4 people. So 12 sigma x divided by n, you end up with 3 slices per person. You're trying to divide something evenly between all of the people in your population. That is one way to look at it. Kind of a more practical way of looking at it. Another way to think of it is the mean as a balancing point. So if we have these, what is this, 1, 2, 3, 4, 5 values, 2 are all the way down here, 2 are values of 6, and 1 is a value of 10. We can see, and here we have our mu, which is either exactly 5 or somewhere around 5. We can say, okay, these 2 values below are 4 points below mu, 3 points below mu, 1 point above each, and 5 points above. And if we add that together, if we add all of the points below, that's 7 points below and 7 points above. So it ends up being balanced. We're trying to find the point where when you add all of that information together, kind of like a histogram, where would be the balancing point that it's equal on both sides? Okay, another thing to take into account is the weighted mean. This is especially important when we have, we're looking at the means of multiple groups, but the size of the groups differ. So for example, group 1 is going to be, if you take stats with me, Dr. Rosenfeld, Let's say we had 29 people in this class. Our n would be 29. And our mu, the average grade, this is just, of course, hypothetical, is 82. Good grade. Now, for group 2, a different class that is taking stats with Dr. Smelly, not a real person, the class size here is 34, so they have 5 more students. And their mu, their average grade, is lower, 71. So now if we want to calculate the mean of both of these groups, we call that the weighted mean. If we want to figure out what would be the mean across both groups, we need to somehow collapse this information together. So we need 2 things to calculate the overall mean. First, we need to get the sum of all of the scores. So all of the scores in class 1 and all of the scores in class or group 2. And then the second, the total number of scores in the combined group, right? How many people? And we have that already here. 29 people here, 34 people here, so we can simply add those 2 together. This is going to be the number that we divide by, right? Because it's the sum of scores divided by your frequency, the total amount of individuals. So if we're going to write that out, the overall mean is going to be the sum of scores for group 1 plus the sum of scores for group 2 divided by both sample means, or not sample means, both samples together, right? 29 plus 34. That's going to be the more simple calculation. So you might think, how did she even get this up here? Because I'm not listing all of the scores here. Well, you can do a pretty simple trick here. This is our mu formula. Mu is the sum of all of our x's divided by n. So if you want to get at what was the sum of x here, you basically can do a basic algebra. Times n over here, then you can delete n. Sorry, I don't have a nice stylus to do this right now. But basically you can come up with a formula that says mu times n equals sigma x. And that's what these are showing here. So mu 82, which is up here, 82 times n for group 1, 72, mu over here, times the n for group 2. Big numbers, add those together, divide them by the 29 plus 34, and we get 76.1. So 76 is the weighted mean of both of these groups together. Separately, stats with me, overall grade 82, stats with Dr. Smelly, it's going to be 71. If we combine both of those together, all of the students, their weighted mean, their weighted average between the 2 classes is 76. And here I'm just writing it out again. The sum of x, so the overall sum for your combined group, divided by the total number in the combined group. So if you have questions about how exactly this worked out, especially this part, just email me, just shoot me a message really quick. I try to, in other slides, write out exactly how I do the calculation. I kind of skimmed over that part, but again, you just multiply by n on both sides, so then you get mu times n, and then you can eliminate the n here, and you're left with sigma x. Okay. All right, let's go through an example. I think many of these are taken from the book, so I'm just walking through the examples from the book. Again, most of us know how to calculate the mean, but I am going to walk through it, especially starting in a tabular format, and then how you would actually do this, because the table does help you visualize it a little better. So these are, let's just say, quiz scores. These are not real quiz scores. All the way down to 6, 1 person had a 6, 8 had a 4, 2 had a 9, and 1 had a 10, right? So if we want our frequency here, these are the amount of people, right? So our n is the amount of people, the amount of individuals. So if we simply add our frequency up, we get the sum of frequency is going to be our n. So 8 people. And now if we want to here, I'm showing the formula for the mean, which is going to be sum of x over n, or sigma x over n. So we have n, which is going to go down here. Now we need the sum of x. And we did this on, was it chapter 2, I think, where we can basically just multiply the frequency by our score, right? So 1 times 10, 2 times 9, 4 times 8. Add all these guys together, we get 66. And then 66 divided by 8 is 8.25. So this is the average score for these individual scores here listed, right? So the average student got an 8.25 on their quiz. Again, not for this class, it's just illustrative. If we wanted to display that, these are small numbers, so we can put that up. The majority got, whole lot of people got an 8 here, 1 person a 6, 2 a 9, and 1 a 10. And our average is resting at 8.25. So again, taking the, I'll show this occasionally. Like I'll display the mean and the data this way because I think it's a very nice way to, as things get complicated. Right now it's kind of easy. It's the average, it's the mean. But as things get more complicated, if you can keep this in mind, it will help. You can see how well balanced this is, right? So the most of them are here. It's going to be a little bit right after, taking into account our larger numbers on each side. Okay, so 4 characteristics of the mean. What happens when we change numbers in our data set? For example, if we change a score, for example, maybe we made a mistake and we have to change a score. So it's not a 9, but a 6. That, of course, you have to adjust your mean. So it's actually going to come down a little bit because it's not a 9 anymore. It was a 6. I guess the person read it upside down. Maybe we want to add a new score or remove a score. So let's say we add a number 6. Now we're going to have to adjust the mean again, right? The mean will adjust with every change that happens, either changing, adding, or subtracting scores. The mean will get adjusted. Now these last two is if we add or subtract a constant to each score, not just a single one, but to all of them. So if we add, for example, +1 to all of them, then we can simply add that same constant to the mean at the end. And I'll show you an example that shows it's as straightforward as that. You don't have to actually go and recalculate the entire mean. Same when it comes to multiplying or dividing. If we're multiplying or dividing every single score by a constant. So we meant it to be, I don't know, I'm not imaginative right now, but I'll show an example in a second. Then you can do the same to the mean. You just multiply it or divide it by that constant. Okay, so this example I think is taken from the book. This was how the color of the text influences your reading abilities. So whether it's a warm color or a cool color. 4 participants. And you have here 11, 12, 14, 11. With the cool color, you may notice, so delta here means the difference, change in or difference between something. So the difference in the colors, in each case, it's +3. So if we were to calculate our mean really quickly over here, excuse me, the sum is 48 divided by 4, we get 12. Here, add them all together, we get 60, divided by 4, we get 15. Now we didn't have to actually, in this case, go and calculate everything because there was a constant of +3 for each of these in the cool color category, So instead, what we can do, we know that constant is +3 for each value, so we simply add that constant to the mean. This mean right here. So we do 12 plus 3. The new mean is 15 for that category. Okay. Okay, so that was the mean. The median is, the easiest way to think of the median is simply the midpoint, the thing that splits the data 50-50. So if the scores in a distribution, this is definition from the book, if the scores in a distribution are listed in order from smallest to largest, the median is the midpoint of the list. More specifically, the median is the point at which on the measurement scale below which 50% of the scores in the distribution are located. So you can think of it as the 50th percentile rank. Right, so as an example, I took here MCU movie runtimes, Marvel Cinematic Universe. This was only up until 2018. I guess Infinity War was the longest running at that time. And you can see here it's sorted from shortest movie, The Incredible Hulk, to, at the time, the longest movie. So the median would be the value which movie corresponds to the score that splits the distribution 50-50. So realistically, just eyeballing it here, somewhere here, Iron Man 3 maybe? Does that seem about right? Yeah, you can kind of eyeball it. Or Spider-Man Homecoming, right? Sometimes people like to do these really beautiful graphs, which look cool. But if you're actually trying to glean any kind of information from this, it gets a little complicated. Sorry, I'm chewing my lips. I think what they're trying to do here is show each phase of the MCU, right? Oh my god, I'm sorry. To like edit that part out or something. And one thing you can see, runtime here, so this is now including Avengers Endgame, longest with 3 hours. You can really see that tail poking out here, but because this is not sorted by shortest to longest, you'd have a really hard time reading this graph properly, or even finding the median, or even the mean for that matter, right? But here it's trying to sort it by the different phases of the MCU movies. But you could trail this all the way back. We'd have to do it from like 2 steps away here, go up to yellow, and then you can see here Avengers Endgame. Okay. Okay. So for this, I was going to have us do this in person in class, but unfortunately we're not meeting in person in class. So what I want you to do, I uploaded an assignment on Blackboard. It's called like social media something. I want you to go on there, and for Netflix, if you don't watch Netflix, just use some type of streaming service that if you don't at all, you can just put in 0, right? Whether it's Netflix or Amazon Prime or Hulu or Apple TV or Peacock. I don't know. Those are, I think, the main streaming services. There's probably others. But for Netflix, for YouTube, and for TikTok, I want you to go on and answer each of these questions. So, if you are watching Netflix, time per item, how much time do you spend watching a particular item? So are you somebody who watches movies? So your average viewing time of one item is going to be maybe 2 hours, or you only like to watch 30-minute episodes of TV shows, or maybe you like to watch kids shows where it's only like 10 minutes, right? So tell me what you think, based on all of your viewing time, is the average length of time that you spend per item, and then total time per day. Right, so average. So of course this might change on the weekend or during the week, but you're trying to figure out an average that you have. Same for YouTube. How much do you typically spend watching, on average, a YouTube video? And then how many hours do you spend watching YouTube? If you don't know, if you're doing it from your phone, you can just look at your screen time and it'll tell you how much time you're spending. And then TikTok. Try to estimate it, they've been changing how long the videos can be on TikTok, so just try your best guess here. Like a minute, you spend only 10 seconds on average viewing videos, and then how much time in total do you spend on TikTok? So I want you guys to do this and upload it. It's a small homework, but I'm gonna put a graph together of everyone in the class, what our general viewing times are like. Okay. All right, so finding the median. So we were talking about the mean. We moved on to the median, which is basically what splits the data 50-50, right? If we're going to have an odd number of integers, these are discrete numbers, it's simply the middle one. It's pretty straightforward, right? We have an odd number here. It's going to be the middle one, 8. If we have an even amount of integers, you're going to take the average of the two middle ones. Again, pretty straightforward. For continuous variables, so here, these numbers here shown over here, it's not going to be as straightforward because these aren't discrete anymore. So interpolation can be used when the median falls within the upper or lower limits of several tide scores. There is a formula for exactly calculating the median, and in this case, it would be 3.75 here, where you kind of have to divvy up, because again, you're trying to split it 50-50. You have 3 blocks over here and a smidge. You're going to have 4 portions of blocks plus another one, right? You're trying to figure out how can I split it. And there is a formula. I'm not going to expect you guys to know the formula, so I'm not walking you through it. Also, since we're not doing this in person, whenever we are going to have the median where I want you to display it in SPSS, there's simply a button that you can click that will show the median for you. I want you to more conceptually know what is the median. Okay. All right, sometimes, this is now when we start getting into distributions that aren't normal distributions but skewed. I want you to start thinking about the relationship of the average and the median, the thing that splits it 50-50. So for example, if we look at this one up here, we have 5 scores all within one another here, 2 or 3, and then one outlier all the way out here. If we were to look at the median, the thing that splits it, we have 6 values, right? 1, 2, 3, 4, 5, 6. So that means the median has to be somewhere between 3 and 4, the average of 3 and 4, right? So the median would be somewhere here, but the mean, the average, is actually lower. So the mean is always going to get pulled to the side of the tail. If we have a skewed distribution, the mean will be pulled to the side of the tail because the mean is much more sensitive to changes, a single change in the score of a distribution. And especially if it's going to be an extreme score, that's going to pull the mean all the way out to that extreme score. Obviously not all the way to that extreme score, but skewness is going to pull the mean around with it. The median is less influenced by it. This is just one score. It's not going to make a big difference. It's still going to keep it here. If this score was all the way down here, the median would still be here, right? So here, for example, I took another skewed distribution, the Scoville heat index for peppers. So, my question to you, I'm going to keep cueing you with this, try to figure out if this is positive or negatively skewed. This one up here, and again, how do you orient yourself on the skewness? Where's the tail going? Where's the tail going? And then if you're trying to figure out where's the mean's going where the tail's going, right? So here, our tail's going off to the left, off into towards 0, so towards the negative here. So this is going to be a negatively skewed distribution. So if we were to try and place the median, let's do the median first. All of these data we're trying to split it 50-50. I would, eyeballing it, say I would put it somewhere in here probably, right? Because we have some over here. I'm just going to put it like right there. But again, your mean is pulled towards the tail of the distribution. So your mean is going to be closer down here, for example. I feel like I'm losing my voice. Okay. So that was the median. The mode's very straightforward. The mode is simply the category with the greatest frequency. So say we have these values here. This guy's your mode. 8 is the most common endorsed score, the most common one that you'll find with the highest amount of frequency, right? 6 is not going to be the mode. The one that basically stacks up the most, has the highest peak, has the highest, greatest frequency is going to be your mode. And just keep this in mind, it's not the actual frequency. It's not going to be 4 is the mode, it's going to be the value here, so 8. And I've mentioned this a couple times now, but this is where the bimodal distribution comes in. So sometimes we have more than one peak. If you remember, I talked a little bit about ice. I like talking about ice cream. America's top 10. So vanilla and chocolate are always the top 2. But it's not that one ever outwins the other. It's actually a bimodal distribution where all the other flavors are kind of like second to vanilla or chocolate. But that you have these, basically the vanilla camp and the chocolate camp. And so those are going to be 2 modes, the max amount of endorsement with everything falling in between. Something like the dress, how do people view the dress? That would also be a bimodal distribution. Mainly because there's no other guesses, like either it's blue and black or it's white and gold to you. Most people wouldn't see this as like pink and green or something. But when you have two items that are selected with the most amount of frequencies, then you refer to those as bimodal. So 2 modes, bimodal. Okay, that was the mode. Like I said, there's not much to say about it. But the rest of this is going to be, how do these 3 relate to one another? When do you use which central tendency, the mean, the median, or the mode? So how do you select it, and how does it influence the shape, or how does the shape influence the distribution of those 3? Okay, so back to this. We looked at this in chapter 2. Symmetry, of course, right? Nice symmetrical normal distribution. Here we have our bimodal distribution, also symmetrical. And again, just to review, when we have a positive skew, the tail, orient yourself on the tail, is going into the positive, so positive skew. Here the tail is going into the negative, it's going to be a negative skew. Okay, so how do, again, these 3 measures of central tendency, how do they fit into the shape of the distribution? Normal distribution is going to be the most straightforward. All 3 of them fall on top of each other. If you have a perfectly normal distribution, that means the mean, the median, and the mode all have the same value. It splits the data 50-50, on both sides. That's the median. It's the peak value, the mode. And if we were to calculate the average, well balanced, the mean would also fall here. Bimodal distribution, as the name implies, we have 2 modes. So one max here, another max here. And then the midpoint of the distribution is going to be in the middle. And if we were to take the average, the median, the mean and the median both fall on top of each other. Something like this, that is not the most natural looking distribution, but we can still talk about it. There is no mode because there's no maximum, but the middle and the average, or rather the midpoint and the average of the scores would still fall on top of each other. Now it's more interesting when we have skewed distributions. And what happens here, our maximum, our mode, our median, what splits the data halfway, and then our mean. Because remember I said the mean follows the tail. So with a positively skewed distribution, where the tail is going into the positive, the mean is going to follow it. Extreme values are going to pull the mean off into that direction. Likewise with a negative distribution, the mode is going to be our maximum, followed by our median, with the mean being pulled into the tail, into the negative, for negatively skewed distribution. So make sure that you keep this order in your mind. Obviously the symmetrical ones are pretty easy and straightforward, but knowing the order with which these 3 measures of central tendency align themselves, you can even do things like figure out what is the shape of the distribution without even seeing it, but knowing what the mean, the median, and the mode is. And I think I'll have an example in a couple slides that shows that. Okay, now when to use each of them, right? So generally speaking, if we have numerical data, the mean is always going to be almost always, the mean is going to be the best, your main go-to gold standard. And we'll see later, it's very closely related to variance and standard deviation, things that are very important when we're doing inferential statistics. So numerical values, specifically interval ratio, right? Median, average, that's the way to go. There are a few times, though, when we're going to use a different central tendency measurement. So when would we use the median? And I was hinting towards this. One of the main reasons we would use it is when we have extreme scores. So here, for example, we have a whole bunch of scores clustered between 10 and 13. But we have one really extreme outlier of 100. And if we keep the data, sometimes we will throw out data if it's an outlier because maybe it's like, not actually possible to get this value and it was an error. But generally we try not to throw out data. So if we have something like this all the way out here, if we were to calculate the mean, our mean would be 20. It would be not even past this breaking point here. And it's not, again, the point of central tendency is to illustrate a point that is representative of the group. And a value of 20 is not representative of this group because this is the group with one outlier. So 20 is not going to be very good here. However, if we take the median, 11.5, smack in the middle here, it doesn't even matter how large this number is. This could be 100, this could be 1,000, this could be 1,000,000, and it would still be 11.5 for the median. So this is a much better representation of this central component, a representative number for this group of individuals or items. So first one, extreme scores. Second, undetermined values. So I think this is an example taken from the textbook, how long it takes a person to finish a puzzle, I think it is, sorted by, or just listed here. It is sorted actually. It's sorted by how long it takes. So the first person, or it doesn't have to be the first person. One person solved it in 8 minutes, 11 minutes. The last person took more than 60 minutes, which is where the experiment stopped. So they didn't have a 0 here, they had a undetermined amount of time, right? Because who knows how long it would have taken them to solve the puzzle. So if you were to calculate the mean here, you can't actually calculate the mean because there's no value here. But if you take the median, you can still take this number into account, and we have 1, 2, 3, 4. It has the number here. We have 6 values, so we're going to take, even number of values, or even integers. We're going to take the 2 middle ones here. So 12.5, right? Our median, doesn't matter how long it took him or her, this person, to calculate, or to, sorry, I'm tired, to finish the puzzle. 12.5 minutes is still going to be a good representative value of how long it takes a person to solve this particular puzzle. And we don't have to throw away this, we don't have to throw away this person's data, but it's a better way of capturing what actually happened. Okay, so outliers or extreme scores, undetermined values. A third one is open-ended distributions. So if you remember with the Boba experiment, this might end up getting covered up, I realize, by my little image of myself talking through the slides. But if you remember with the Boba, I had one category that said above 50. So, above 50 could mean 51, it could mean 100, right? And not knowing the exact value, you cannot calculate the mean because you cannot add all of your scores together. Again, though, the median can simply smack it in the middle and say this is going to be our representative value. Even if we don't know what those higher values are, at least we have something that we can work with that still represents the majority of the group. Okay. So those were all numerical data, right? Numerical with extreme scores, numerical data with values that we don't actually know. Same here, values we don't know because it's open-ended. And this one here, there's another one, if it's ordinal data. So we know the direction, but the distance between measures is unknown, right? So median, because we don't know the distance, it's not actually, again, possible to calculate the mean. But the median can show us where does that 50-50 mark fall on, even if we don't know the exact value because it's ordinal data, it's non-numerical. So there are times when the median can be highly useful, and often we'll still, if it's even physically possible to calculate the mean, we still will, but as a representative value, the median is going to be more informative for these cases. Okay, so when would we use the mode, right? It's like seems kind of a throwaway, like why bother? So these are going to be more for example, a non-numerical scale of measurement, such as nominal scales, right? Like the ice cream flavor favorites that I showed. Or from the last chapter, theme parks, right? There's no really way that we can put a quantitative measure of how good Disney is versus Universal Studios, right? So there we would use the mode, right? More people go to Disney than they do to Universal. So there, a mode would be more representative of what the average or the general person is going to be doing. And again, the mean and the median might actually be physically impossible to calculate because these are non-numerical. Also, if we have discrete variables where we cannot divide them, we can't make fractions like with people. How many siblings do you have? You have 3 siblings. So if you were to calculate the average or the mean, having 1 3/4 children doesn't make sense. So instead, we're going to use the mode to better talk about it. So for example, of the 4 children, 2 usually get chocolate ice cream, 1 gets vanilla, and 1 gets strawberry. So chocolate is the typical or modal ice cream preference of these siblings, right? Because fractions just wouldn't make sense in this case. You could certainly calculate it, but it's all nonsensical. Also, describing the shape, because it's the maximum value, can be very informative. You know, kind of what is the majority doing in a particular example. And this is what I was hinting at. So for example, if you have the scores, you have the mean and you have the mode, you can kind of figure out in your head what the shape of the curve is, or the shape of the frequency distribution is supposed to look like. So here our mean is 72, our mode is 80, right? So our mode is higher than our mean. So this should be enough for you to figure out whether or not this is positively or negatively skewed. So try and think about that for a minute. The mean is always going to be pulled towards the tail. So I'll let you think on that. Email me if you want to know the answer. But I want you to, again, I'm always kind of triggering you guys to think about the skewness. Okay. Means and medians and graphs, that's how we started this lecture, right? Is that we're going to have something that ideally represents each person, each category, or here each drug dose. So whether it's an average or a median, we can display that in graphs. So here we're talking about drug dose or categories. You know, these are going to be, in this case, our IVs, our independent variables, the things that we can manipulate. Do we give someone 2 doses or 1 dose? And DV is the thing you're measuring, right? Here, the thing you're measuring, even if it's sideways. So this is a nice way that we can start having kind of a more scientific depiction of our data. Very typically, these are going to be means that we're displaying here. Yeah, and so that's what we were talking about in the beginning, where each dot or circle or square actually is a representative score. And like I said, typically it's going to be the mean or the average. So when it comes to nominal or ordinal scales, remember we prefer to use bar graphs for these. Bar graphs look like histograms but with spaces in between them. The spaces are really to indicate that these guys don't neighbor each other, right? Either you're in preschool, you're in elementary school, secondary school, but there's no distance between them that you can define properly. So when you're doing something like this, a bar graph for nominal or ordinal scales, will also often frequently, in this case, this is income, right? Frequently, we're not going to use the average income because there are billionaires out there, right? Unfortunately, income in the United States is not normally distributed. It is highly skewed. And so because we have extreme values, it's better to use median scores as a representation. So you can see here median weekly income. That's going to be better because if it's the average, it's just going to be pulled up way to a value that the average person doesn't actually make that income, right? Again, you're trying to think of what is the typical person, what represents the typical person. Okay, so I think that was it for chapter 3. Whew. I hope I wasn't talking too fast through all that. I hope that made sense. The next chapter is going to be after exam 1, but that will talk about variability. So there we're going to start talking about variance and basically things that can manipulate the shape, not skewness, but kind of like, is the curve pointy or is it flat, and what influences that. But for now, that's chapter 3. If you have questions, of course, please email me, and I will see you guys next week.